Welcome to another video from the Heart Factory. In today's video, we'll be talking in detail about the oxygenators and its various functions. The first few minutes of this video will be in mute and will be detailing the various parts of the oxygenator and the hemotherm for your better understanding during the last half of this video. So let's get started without wasting much time. The term oxygenator has come to mean that portion of the perfusion apparatus that serves the function of the patient's natural lungs during the period of cardiopulmonary bypass. It also transports carbon dioxide, anesthetics and possibly other gases into and out of the circulation. All modern oxygenators have integral heat exchangers and also serve as the main reservoir and a filter for blood returned from the cardiotomy suction. So if you look at the oxygenator, it performs all major functions of the natural lungs except for their endocrine function, which I guess can be suspended for the short duration of time the patient is on cardiopulmonary bypass without any ill effects. These oxygenators are designed in a way that the amount of oxygen, carbon dioxide and other gases that can be transferred at a given blood flow rate are maximized to make gas transport easy to regulate, to maximize heat transfer efficiency, to minimize blood trauma and to minimize the priming volume. Now, gas transfer from the gas to the liquid phase or from the liquid to the gas phase is driven by diffusion and is based on the partial pressure difference of a particular gas. The ideal oxygenator would transfer oxygen into and remove carbon dioxide from the blood at physiologic blood flow rates with very minimal trauma to the blood and with a very small priming volume. So gas transfer across an oxygenator is directly proportional to the partial pressure difference of the gases and surface area and inversely proportional to the distance of diffusion. Compared to a normal lung, the oxygenator surface area is only about 10% and it overcomes its shortcomings in terms of surface area by increasing the distance that the blood would travel within the oxygenator for gas exchange to happen. The amount of time the blood is taking to travel within the oxygenator is increased, thereby increasing its chances to exchange the gas, which is called an dwell time. A phenomenon called secondary flows are induced within these oxygenators to promote mixing and bring deoxygenated blood closer to the blood-gas exchange surface. Now, none of the oxygenators in the market can ever match a natural lung, but the hypothermia, the muscle paralysis and anesthesia that the patient is subjected to will reduce the patient's metabolic requirements to the extent that the oxygenator is sufficient to perform its job. Now there are three types of oxygenators known. The first is the film type or the original Gibbon type of oxygenator. The second being the membrane oxygenator, which is quite common in the current era, and the bubble oxygenator. The membrane oxygenators are the most commonly used ones in current era because of its advantage over the bubble oxygenators for reducing blood trauma and the risk of embolization. They have three compartments, each for blood, gas and water. Now gas and blood are partitioned into separate compartments with either a limited or absent blood-gas interface. Now the membranous oxygenators have microporous membranes that allow at least a transient direct blood-gas interface at the start of cardiopulmonary bypass. Now after a short period of time, protein coating of this membrane occurs and there is no further direct blood-gas contact. A thin layer of proteinaceous material covers this membrane and it forms an area over which diffusion of gas happens. The micropores provide conduits through the polypropylene membrane that gives sufficient diffusion capability to the membrane for both the oxygen and carbon dioxide exchange. Under normal circumstances, blood surface tension prevents gas leakage into the blood. The membrane oxygenators imitate the lung by having a thin membrane that could either be made of polypropylene or silicone rubber or polymethyl pentene, may have pores or may not have pores, may be a true membrane, and may be configured in various types like the scrolled envelope pattern, parallel plate pattern or the hollow fiber type. Now coming to the hollow fiber type of membrane oxygenators, the hollow fibers may either have blood within them or blood outside them. Mixing is achieved by winding of the fibers, creating a crossing pattern and increasing exposure of the blood to the membrane surface. These hollow fibers are employed to separate the blood and gas phases, and the number of fibers utilized will vary depending on the total surface area that is required for gas exchange. The fibers are capped on each end with a polyurethane material and are typically in the range of 200 to 300 microns. The pores in these membranes are developed by stretching them, and the pores are usually around 0.03 to 0.07 micrometers in effective diameter and cover at least 50% of the membrane surface. Now as the surface area of the oxygenator increases, the volume of solution necessary to prime the system also increases. Now the contemporary design of hollow fiber membranous oxygenators have blood flow around the hollow fibers with gas flowing through the fibers. Oxygenators with longer blood flow paths will require less fiber surface area. The oxygen enters one end of the bundle of the hollow fibers and exits at the opposite end. Oxygen and carbon dioxide diffuse in opposite directions across the surface area of the hollow fibers. Gas transfer in membranous oxygenators is a function of several factors that include surface area, the partial pressure of venous oxygen and carbon dioxide, the rate of blood flow, the ventilation flow, the so-called sweep rate, and gas flow composition. Partial pressure of oxygen is a function of FiO2, whereas the partial pressure of carbon dioxide is determined by the sweep rate of the ventilating gas. So, there is an independent control of ventilating gas that results in ABG values closely resembling normal physiologic blood gas status. Having said this, whilst on cardiopulmonary bypass, it's very common to find the PaO2 levels in the range of 250 mmHg plus to adjust for the hemodilution and the limited reserve capacity of the membrane oxygenators. The oxygenator represents the largest source of non-endothelialized surface area in the whole cardiopulmonary bypass circuit, and therefore it is important that the device is meticulously primed to remove all residual air before establishing cardiopulmonary bypass. In an effort to reduce the surface area exposure and prime volume, newer generation oxygenators have inbuilt arterial filters. The membrane oxygenator circuit is designed to include a recirculation line from the arterial outlet of the oxygenator to the venous reservoir. Now, as discussed in my previous video, this line is important to de-air the circuit. It is the line that provides oxygenated blood to the cardioplegia circuit. It is the line that allows continuous reperfusion through the arterial and venous reservoir in patients who are under total circulatory arrest. It is a circuit which can eliminate air that has accidentally entered into the cardiopulmonary bypass circuit, and it is set to assist in case of an oxygenator malfunction. Now, coming to true membrane lungs, they are the ones which provide a complete barrier between the gas and blood phases, so that gas transfer depends totally on diffusion of gas through the membrane material. They are expensive and have a large priming volume and are approved for long-term support, such as that seen in the ECMO. The important aspects of microporous membranous oxygenators are that there is an absence of direct blood-gas interface once the proteinaceous coating happens. It provides a high resistance to flow, therefore membrane oxygenators are always placed in front of the roller pump and blood has to be pumped actively across the oxygenator. The pressure gradient across a membrane oxygenator is to the range of 100 centimeters of water, and it's around 30 centimeters of water in a bubble oxygenator. Independent regulation of the partial pressure of carbon dioxide and oxygen is possible by varying gas flow rate and FiO2 with membrane oxygenators. Now, the gas flow through the membrane oxygenator is often referred to as the sweep rate. Higher rate of gas flow will eliminate more carbon dioxide from the membrane surface, thus increasing the gradient from the blood to the gas phase and thus decreasing the arterial PCO2. So the ideal oxygenator would be one which oxygenates venous blood, eliminates carbon dioxide with minimum trauma to the blood that is induced by direct exposure of the gas to the blood, has a smaller priming volume which has impact on hemodilution and protein concentration, and one which is highly accessible, visible and safe with a very less possibility of air embolism. The most influential factor that affects blood trauma in an oxygenator are related to how blood traverses the device and are termed shear stress and stasis. Heat exchangers basically transfer heat from higher temperature to lower temperature. Heat transfer occurs in three forms. Either it is conduction that happens through solids, or convection that happens from solids to liquids, wherein the liquid is moving away from the solid-liquid interface. And the third mechanism of heat transfer is by radiation, an electromagnetic mechanism. Within the CPB heat exchanger, the major form of heat transfer are forced convection and conduction within the stainless steel. Now, these heat exchangers are integrated into commercial oxygenators to permit out-of-the-body cooling and warming of the bloodstream by varying the water temperature flowing into the heat exchanger. The exchange surfaces typically are made of stainless steel or aluminium and have fins to maximize the efficiency. In case of the Lilliput or the oxygenator used in pediatric age group, the heat exchanger comes as a separate unit and has to be accommodated into the oxygenator. So the heat exchanger and the oxygenator are two separate units which after assembling form a single unit. To prevent formation of gaseous microemboli, the temperature gradient between the water and the blood does not exceed more than 10 degrees centigrade. Generally, the heat transfer into and out of heat exchanger is provided by non-sterile water that is circulated through a heater or a cooler unit, which is part of the perfusion apparatus. Now, when cooling is desired, the water is passed through an ice bath, and when warming is desired, it is heated by electric heaters. Now, water as a heat transfer fluid is simple and reliable and provides an even temperature distribution across the surface of the heat exchanger without localized hot spots. Now, heat transfer surface is usually made of stainless steel or aluminium, with stainless steel being more durable and chemically inert of all the commercially available heat exchangers, but is expensive. Aluminium, however, has a higher toxicity in humans, and levels of aluminium more than 200 milligrams per liter are said to be toxic to the human body. Now, both aluminium and stainless steel have good thermal conductivity and are readily coated with polymers to minimize blood interactions. To maximize heat efficiency of heat transfer, fins that extend into the blood are developed. Heat exchange is also enhanced in most of these devices by flowing the blood and water in opposite directions, the so-called countercurrent heat exchange. Now, rapid cooling is commonly used at the onset of cardiopulmonary bypass when circulating water is cooled to temperatures approaching 3 to 4 degrees by an ice bath, thus rapidly cooling the blood. At the conclusion of cardiopulmonary bypass, the rate of rewarming is limited by concerns regarding blood damage due to overheating and bubble formation because of the lower gas solubility of warmer blood. Blood damage in the form of protein denaturation limits the absolute maximum temperature to 42 degrees centigrade in this hemotherm. In addition, the maximum difference in temperature between the water and the venous blood is limited to prevent bubble formation due to rapidly decreasing gas solubility. The gaseous microemboli formations can be avoided by limiting the water and or blood temperature difference to 10 degrees centigrade. Now, the effectiveness of a heat exchanger depends on several factors, including the total surface area, thickness of the conductor walls, thermal conductivity, and the residence time of blood through the device. Heat exchanger basic design consists of two phases, with water passing on one side and blood or perfusate on the other side. So the direction of blood flow is routinely countercurrent to the flow of water, which optimizes heat transfer. The temperature of water entering the heat exchanger is controlled by an external cooler or heater device, as said before. The majority of heat transfer, as said before, occurs by conduction or convection. Therefore, all heat exchangers for the cardiopulmonary bypass circuit possess a high degree of chemical inertness. They are highly resistant to corrosion. They have a smooth surface. They have a low energy surface where RBC and plasmatic residues do not adhere. They provide low resistance to blood flow. They require very small volume to prime and are disposable. In bubble oxygenators, venous blood drains directly into a chamber into which oxygen is infused through a diffusion plate. The diffusion plate produces thousands of small oxygen bubbles within the blood. Now, gas exchange occurs across a thin film at the blood-gas interface around each bubble. Carbon dioxide diffuses into the bubble and oxygen diffuses outwards into the blood. The bubbles are in direct contact with the blood with essential features that include an optimal mix of bubble sizes because smaller bubbles exchanged oxygen well and the larger bubbles exchanged carbon dioxide well. Bubble oxygenators have very low resistance to flow and have a very low pressure drop across the oxygenator in a way that gravity and bubble flow can drive gas exchange. In a bubble oxygenator, there is a need for a settling chamber with an anti-foaming material to defoam the blood before it's being reinfused into the patient. Oxygen and carbon dioxide exchange is more interdependent in bubble oxygenator than in a membrane oxygenator, with increase in gas flow increasing the PaO2 and decreasing the PCO2. One has to maintain an adequate reservoir volume in a bubble oxygenator to allow for adequate blood gas exchange and debubbling of the blood. If you like this video, please click the like button and subscribe to my channel. Don't forget to click the bell just to be notified of my next video in time. I would really appreciate if you can leave some comments for all of us to learn, and also request you to keep watching this space for future videos. Thanks for watching. Thank you.